Welcome to today's paper reading. Today's paper is titled, LLMC, LLM Do, Guiding Data Generation to Target Non-Differentiable Objectives. This paper was published on the AR14 preprint by Luísa, Shimabucoro and colleagues from Cohere for AI. The abstract discusses the impact of synthetic data on large language models, LLMs. It highlights how synthetic data can influence a model's internal biases, calibration, and the attributes of its generated text. The study finds that models are sensitive to certain attributes even when synthetic data prompts appear neutral, raising questions about whether this sensitivity can be leveraged for beneficial purposes. The abstract also introduces the concept of active inheritance, where synthetic data is intentionally constrained to achieve specific non-differentiable objectives, such as high lexical diversity or low toxicity. This approach challenges the historical assumption that it is infeasible to steer models towards desired properties at test time due to the cost of collecting data with specific characteristics. Historically, the curation of high-quality labeled data has been hindered by the scarcity of available data and high financial costs. This has led researchers to treat datasets as static rather than malleable. Recent efforts have focused on optimizing the use of existing data through methods like data augmentation, pseudolabeling, and data weighting. However, these methods still rely on enhancing a fixed dataset. In contrast, synthetic data generation offers a way to rapidly shape the data space with latent, desirable characteristics such as increased length, lexical diversity, and low toxicity. This approach allows for the steering of model behavior towards non-differentiable objectives, which is typically achieved through more complex methods like reinforcement learning or Bayesian optimization. Our study introduces the concept of active inheritance, where we steer iterative synthetic data distillation towards specific characteristics, enabling significant gains in desirable attributes and reductions in undesired ones. Figure 1 illustrates the percentage change in various attributes of a model after it undergoes synthetic data distillation. The study highlights that through a targeted sampling approach known as active inheritance, the model's behavior can be steered towards discrete preferences. This method effectively enhances desirable attributes such as length and diversity, while simultaneously mitigating negative attributes like toxicity. The strategies employed include both single-source and multi-source sampling methods, demonstrating their efficacy in achieving these objectives. In the methods section, the authors describe the process of knowledge distillation, where a student language model, LLM, is fine-tuned to maximize the log likelihood of a teacher's generated sequences. This process uses the teacher's generations as a proxy for a gold sequence, forming a synthetic dataset for optimization. The authors also introduce the concept of active inheritance, where proxy labels are selected based on their presence of desired characteristics, using a best-of-case sampling strategy to directly guide the amplification of these properties. Additionally, the authors explore learning from multiple teachers, leveraging an ensemble effect with diverse teacher models to maximize the chance of obtaining high-quality samples. Table 1 provides an overview of the profiling toolbox used in the study. It categorizes metrics into textual characteristics, social bias, and toxicity. Textual characteristics include metrics like length, gunning fog, RIX, and MTLD, which measure aspects such as length of generations and textual lexical diversity. Social bias metrics include stereoset, Kreutzer pairs, and barbecue, which assess stereotypicality of associations and bias in question answering. Toxicity metrics, such as RTP prompts, expected maximum toxicity, and toxicity probability, evaluate worst-case toxicity and the probability of toxic generations. The details of these metrics are provided in Appendix B. Figure 2 illustrates the changes in model profiles after fine-tuning large language models, LLMs, on synthetic data. On the left, the social bias scores for the barbecue benchmark show a general decreasing trend for Llama 2-13b, with the exception of the disability metric. In the middle, there are minor changes in the measure of textual lexical diversity, MTLD, and the readability index, RIX, accompanied by a significant increase of over 100% in the mean number of tokens. On the right, toxicity metrics worsen across all cases after fine-tuning, with increases up to 40%. This figure highlights that models are prone to substantial changes, and the direction of these changes is not always predictable. Table 2 analyzes how attributes of LLMs as evaluators change based on synthetic data sourced during fine-tuning. Metrics include human agreement, length bias, and preferences for Mixtral and Llama 2 models. The data origin significantly influences the direction of these attribute changes, showing both positive and negative trends depending on the data source. Figure 3 illustrates the agreement rate between models before and after data distillation. It shows that training on synthetic datasets generated by other models increases intermodal agreement by up to 13.2%. Self-distilled models maintain over 80% agreement with their teacher models. Additionally, fine-tuning on Mixtral's data increases human agreement by 2.7%, contrasting with a decrease when using Llama 2's data. In this section, we discussed the experimental results focusing on the influence of data distillation on model preferences. We observed a significant increase in intermodal agreement by 13.2% after data distillation, particularly for models trained on synthetic datasets generated by other models. Self-distilled models maintained a high agreement rate above 80%, indicating a strong retention of the teacher model's preferences. Regarding human agreement, models fine-tuned on Mixtral's data showed an increase of 2.7%, while those using Llama 2's data experienced a decrease of 5.67%. This difference can be attributed to Mixtral's larger effective size and higher quality generations. Additionally, we explored active inheritance methods to enhance specific attributes such as length, lexical diversity, and toxicity. Both single-source and multi-source sampling strategies were employed, successfully steering the models towards the desired generation profiles. Figure 4 compares active inheritance methods, specifically single-source and multi-source sampling, aimed at improving various metrics. The primary objectives are to enhance the length and lexical diversity of outputs while reducing toxicity. The analysis demonstrates that both Llama 2 and Mixtral models effectively align with these goals, showing successful steering in the desired directions. Table 3 presents an analysis of the changes in three targeted attributes: number of tokens, NTLD, and toxicity, after fine-tuning base models using curated datasets. The results are shown for both single-source and multi-source sampling strategies. The findings indicate successful installation of desired attributes, demonstrating both positive amplifications and negative reductions. Specifically, the multi-source strategy shows significant increases in the mean number of tokens per generation, with at least a 66% increase compared to the base model. Additionally, the mean MTLD score increases by 8% for Llama 2-7B and 15% for Mixtral 8x7B, with substantial improvements over the baseline. The study also highlights the potential for curated synthetic data to mitigate undesirable characteristics, such as reducing toxicity by at least 20%. Figure 5 analyzes the impact of filtering an increasing number of candidate samples per prompt on lexical diversity and length gains in a multi-source setting using Llama 2-7B. The colored bars represent relative gains, while the hatched gray bars indicate the random sampling baseline results. The study reveals that while there is no clear correlation between higher sample availability and greater length gains, the effect of active inheritance on lexical diversity increases with more distilled samples. This suggests that while some attributes benefit from a larger sample pool, this is not universally true for all objectives. Table 4 presents examples of how large language models, LLMs, prompt completions change before and after they are fine-tuned on specific synthetic datasets. This fine-tuning process aims to enhance the model's responses by training them on targeted data, thereby improving their performance in generating more accurate and contextually appropriate completions. In the related work section, several key studies are highlighted. First, Jinma and Fu et al. Introduced instruction tuning in 2023, focusing on the GPT score tool for flexible evaluation. Second, Liu Gao et al. Developed a framework for few-shot language model evaluation in 2023, accessible via the URL provided. Lastly, Fabrizio Gilardi et al. Demonstrated that ChatGPT outperforms crowd workers in text annotation tasks, as published in Proceedings of the National Academy of Sciences in 2023. In this conclusion, the authors highlight the use of Bayesian optimization for algorithmic testing, as presented in the 2018 Advances in Neural Information Processing Systems, Volume 31. They also reference a comprehensive survey on knowledge distillation by Go et al., published in the International Journal of Computer Vision in 2021. Additionally, the authors acknowledge the collaborative efforts of Groeneveld et al., including contributions from Isbeltagi, Pete Walsh, and others, demonstrating a multidisciplinary approach to their research. Thank you for watching.